So maybe let's see if we can have today a lecture that connects back to what Matthias Hein is currently doing in the statistical machine learning class and gets a bit more hands-on and maybe easier to understand. What I want to do today is really dive into the core questions of machine learning, the central tasks of learning machines, learning functions. And we'll do that from the probabilistic perspective. It turns out that the mechanism to describe the process of inference on functions is extremely, centrally linked to this Gaussian inference mechanism that I have already spent the last 2 lectures introducing. So here's a quick summary again. Gaussian probability distributions, probability density functions, Gaussian measures are the workhorse of practical statistics, machine learning, inference, computational statistics, whatever you want to call it. Why? Because they have extremely useful algebraic properties. A product of 2 Gaussian probability density functions is another Gaussian probability density function up to a normalization. Linear projections of Gaussian random variables are Gaussian random variables, and the transformations involve only linear algebra, applying matrices to vectors and matrices from both sides, or linear operators if you like. Marginal distributions of Gaussians are Gaussian random variables are Gaussian random variables. So we can effectively implement an get item method for our class of Gaussians, select elements. This is a very powerful property because it means you can reason about very many variables, and then if you care about only one of them or a subset of them, you literally just have to look at subsets of their mean and covariances. And most importantly, the conditional distribution of a Gaussian random variable when conditioned on a linear observation of another Gaussian random variable, or sorry, maybe that's actually the correct statement, is another Gaussian random variable with parameters, posterior mean and posterior covariance, that involve basic linear algebra operations, so matrix inverses applied to vectors and matrices. And perhaps as an interesting side observation, the quantities that are sort of creating the complication here, the complicated bits, the matrix inverse, shows up both in the mean and the covariance. And that means that we can use computational resources spent on computing this point estimate, the mean, to also compute posterior uncertainty, posterior covariances. And that means 2 things. A, that we can transpose this abstract philosophical notion of Bayesian inference onto linear algebra if we commit to using Gaussian probability distributions and linear relationships between variables. Linear algebra is a powerful tool. We can use it for, we have all sorts of beautiful tools to perform these computations on computers. So that allows us to do very efficient things. And the other thing we noticed is that what's sort of indicated here on the right, that we can translate these mathematical statements into concrete code, array-centric code, if you like, that translates these operations into the standard operations that you may know from array-centric code. So you can take this as motivation in either direction. So if you've wondered why NumPy looks the way it looks, it's maybe to some degree because of these properties. So the question then is, now that I've harped on so much about this for 2 whole lectures, and the last time actually maybe ran a little bit too far away from you with the stuff that I got excited about, what is this actually useful for? Well, it turns out the one main thing, maybe the main thing it's useful for, is for learning functions. And because functions are a super fundamental object in math, and in the description of the natural world, any quantitative description of the stuff around us, that's an extremely powerful thing to do. So today, and the next few lectures, we'll spend a lot of careful time doing sort of the opposite end of what Matthias Hein is doing in his lecture, with this sort of abstract notion of what you're trying to do, and then hopefully it'll work. Here in this lecture, we'll instead look very deeply into how you do actually do the computations to learn a function, and what kind of degrees of freedom we have there concretely in the code, in the modeling language. But I'll start, of course, with an extremely simple function. We kind of have to, right? The very first function to look at is going to be something like this, which actually isn't a function, right? So that's going to be the first observation. The typical setting in machine learning, our textbook idea of what we're trying to do is we have a finite amount of numbers, data, that has been collected. And those numbers come to us in the form of pairs, input and output pairs, x and y, right? And maybe if you're a good scientist, you've also recorded the fidelity with which you've collected this data. So there are some error bars that you can see, right? You kind of know, okay, I don't perfectly know what I've measured with a little bit of measurement error. Right. So this is obviously a super banal setting, but it's actually the kind of setting that emerges in some very basic, admittedly, problems. So for example, here is a picture of my former colleague and friend Jeanette Boog working in Tübingen with a robot, an old one, like from the early 2000s. Of course, these days they all look so fancy and menacing and dangerous. Like back then, they tried to look very, very funny. One of the earliest things you do when you set up a robotic system like this is that you have to build a kinematics model. So this robot consists of a bunch of motors. Every single joint here is one electrical motor. Electrical motors are machines that turn current into, or actually voltage, into torque, right? So, but you need to know how to get from voltage to torque. There's just an unknown proportionality constant. And for that, you do a measurement like this, right? You collect a bunch of measurements of the torque with some sensor as a function of the voltage that you put in. So you can imagine positive voltage means the motor wants to turn one direction, and negative voltage means it wants to turn the other direction. So I'm also going to load, by the way, this data set, so we can already start doing this kind of business. So what I'll do today is we'll work with a data set that I have put also on Jupyter Hub in the form of a bunch of CSV files that I'm reading in here that consist of x and y's. So for those of you following along, you know that this is called a supervised learning problem, right? Where we have labels and inputs. And we can load them. And then this plot that you just looked at, I made by running literally this code. Right? And now the question to you, of course, is, there is clearly, I mean, clearly the setting is that there is a function underneath here. When people draw an error bar, engineers, that means they're making a Gaussian assumption. Right? They are saying that the measurement, each y value was measured with Gaussian noise, Gaussian uncertainty of some standard deviation. The width of the error bar denotes the standard deviation. The little dot in the middle denotes the mean. And the question is, there is clearly a function underneath that maps from x to y. What does that function look like? To make sure everyone's following along. What's your proposal for the function?
Assuming it's linear, it's probably somewhere around -10 plus 2x.
Ha! So you said it's linear, and you said something like -10 plus 2x. Where did you get the -10? So -10 is over here?
2x minus 10.
Ah, 2x minus 10? Yeah, so the zero, the coordinate axis is somewhere here in the middle, so the intercept is probably something close to 0. Let's say we don't exactly know what the intercept is, so it's something unknown, right? So it's a linear function. Good point, yeah? So first of all, here's the situation. We are getting inputs and outputs. So here's a graphical model, a directed graphical model that you've seen in your first exercise sheet. The two black circles indicate that these are the things we know. And then there is an unknown thing in the middle that is a function. But writing f for a function is maybe at this point, at least in the lecture, a little bit too much. Like, we don't know what that should be. So the proposal is, it's a very good proposal, to make a concrete so-called parametric assumption about what the function looks like. So we're going to say there is a linear function here, one that maps from x, it's linear in x. Right, that maps from x to a constant plus another constant times x. So we can think of the situation like this. We're getting an input, and we're computing x and another 1, and then we can write y as, oh, that's badly done, w1 times 1 plus w2 times x. Right? So I'm deliberately going very slow. If this seems super tedious to you, just nod vigorously that you're understanding. So pretty obvious. Yeah? Okay, good. So now the next mental step, maybe it's just good to do this once very slowly, right? Although, of course, many of you have seen a deep learning class and so on. So the next mental step to do is to say, we can think of this black stuff that we're computing here as a bunch of features that we are computing. So we're taking in x, and we're computing 2 features of x. The first feature is x itself, and the second feature is just a 1. It's a trivial feature, but whatever, right? It's still a feature, just to compute. So we can take x and produce this vector 1 and x. Then we can take the elements of this w, stack them also into a vector, and then we can think of this function as evaluating this inner product. So what this highlights, this way of writing things, is that this is a linear operation, not in x, but in w. Right? We are now computing a linear map of w. Because there's a vector w that enters inner product. Right? It just so happens that this function of x is also a linear function of x. It computes x and 1. But just about 5 minutes from now, we'll forget about that. But the important thing is that it's linear in the weights w. So now, question to you, how can we use these Gaussian mechanisms, this wonderful stuff that I just showed you before, this very dense, busy slide, to build a mechanism to do inference on this unknown function? So first of all, what's the unknown thing in this function? The weights, the w's, right? So we know x, we know y, we want to know w1, w2. Okay, so what are we going to put the probability distribution over? Over w. What kind of probability distribution are we going to put over w? Someone else. Make it easy for yourself, just to get you all excited on a Tuesday morning. A Gaussian distribution. Okay, so then, why are we using a Gaussian? What can we do with this setup? Which property here can we use? Which of these 4 dots can we use to do inference? The second one, yes. Because what we're making is a linear observation. We're taking this phi vector and we're multiplying it from the left. So our phi will be the a in this thing, right? So we take our, let me actually do this. We will take a Gaussian distribution over the weights. Here is a Gaussian distribution over the weights. It's a 2-dimensional Gaussian distribution. I've actually picked the standard Gaussian distribution, just mean 0, covariance matrix 1, because whatever. And now we're computing this vector phi, and we can compute this vector phi of x for every single x in some space of x's. And then we apply this vector phi to our Gaussian. We know how to do that. And we'll get a Gaussian distribution over the values of the function f of x for every possible value of x. In fact, we'll get a joint Gaussian distribution over all the values of this function at arbitrary points x. And this is what I'm plotting here. So, I mean, the black stuff is still the data. And behind, what you're seeing is for every single value of x, I have picked the corresponding x, fed it into this function phi of x. It has returned x and 1. I'll multiply it from the left and right onto the covariance, or from the left onto the mean. I'll get out a new mean. So if mu is 0, what is my mean going to be? Yes, 0. And that's what you see here, right? There's a line in the middle that is 0. That's our mean for the function values at arbitrary points x. And then I'm computing phi x transpose sigma phi x for this feature function phi x. So remember, the feature function is just x and 1. Should we do this on a... So we're going to multiply from the left the function 1x onto this covariance matrix. What is this? Yes, in the back. X squared plus 1. And then why does it look like this background, this grayish background? Because I'm plotting the standard deviation, which is this. And that's what this curve is that you see here. That's it. So did I make this plot? Actually, okay, do I show you the slide? I first show you the code, and then we go back. We'll go very slowly. So to do this, I load the Gaussian class. I've updated this class a little bit. Every lecture it gets a little bit longer. That's why it's called Gaussian Lecture 05. I encourage you to have a look. I added a bit more stuff, but a little bit more helper functions. But in general, it's the same thing as before. It still has this mean and this covariance. I said my prior is going to be this Gaussian distribution with 0 mean and standard covariance, 2 parameters, W1, W2. And now I'm defining this feature function. Now, unfortunately, of course, in Python, this looks a bit ugly. So what I'm doing is I'm writing a function that takes in x, and then it returns ones and x's of the same shape as x. So if I give in 20 different values of x, I'll get 20 ones and the 20 different values of x underneath each other. Now I decide where to plot this stuff. So I say I want x to be numbers between -5 and 5, 100 of them, please. Make them in the right shape so that everything works out. Evaluate this phi and map it from the left onto the prior. So what kind of data type is this? It's a Gaussian with a mean and a covariance. And what does it look like? What do you want to see? Did I type it right? No, it's difficult to type behind your back. So it's all zeros for the mean. And then we have this complicated covariance, right, which starts up here, 26, 25. They're all co-varying with each other, these function values. And they look like this. So here what I've plotted is literally just the mean plus minus 2 standard deviations filled in with gray in between, and 3 samples from this distribution. So those samples, they are basically samples from the weight space. But actually, I don't draw from the weight space, right? I draw from this joint Gaussian. I draw from this object that is 100 by 100 dimensional. And what I get is these 3 gray lines. Who finds it surprising that they look like straight lines? No one. Everyone's completely right. So it's kind of cool, no? So we decided that there is this 2-dimensional space that they come from. It's just 2 numbers that we don't know. And now one way to get these lines is to draw in the weight space. And this is actually what I've done here for this plot, right? You could draw 3 points, 1, 2, 3. And then each of these points in W space corresponds to a function of x. This one, which one is this over here? Can someone tell me? Oh, W0, W1, I'm off by 1 problems with my indices, but whatever. Yes? Mm-hmm. So it's the one with the positive slope that passes below 0, right? Because W0 here is negative, so we have to be below 0 at 0. And W1 is positive, so we have to have something that has a positive slope. That's this function. And here is the other extreme, is something that has a positive W0, so it passes above 0 at 0, and it has a negative slope. That's this one. Those are the exact same things. But you can make this plot by creating this Gaussian object that I just made and drawing from it, and then you'll get this gray line. Yes? Yes, yeah. So I'm sorry about that. I made the plot and then I made the slides and then I got off. Like I have I'm off by 1 error. So 0 and 1, whatever, plus 1. But there's just 2 of them, right? So it's easy not to get confused. Okay. So now what we've just built is a prior distribution for a function. So far, the data hasn't been used yet, right? It's just a prior distribution. So here is a slide that I usually have to show at this point that tends to somehow confuse people, but I also feel like I can't quite not show it. So I want to emphasize this notation again that we're using here that translates from these ideas of functions into this array-centric programming that we're using here. So what I'm doing is I have a data set that consists of pairs of x and y's. And I'll put them into a stack, right? So one vector of x's, one vector of y's. Now I want to describe a function that maps from x to y. And the way we do that is to create features, phi of x, which are functions that take in an x and then they return a vector themselves. But of course, I don't just want to do that for a single value x. I want to make plots like on the previous slide. So I'm going to have to deal with lots and lots and lots of different x's, which is why I will actually call this function on many x's. And then what Jax will do for me, or NumPy would do, is to broadcast the different x values into this function phi of x. And what I'll get out is a matrix of size number of features by number of inputs, f by n. So if I pass in 100 different x values, I get out a matrix of size 2 by 100. The first row of this 2 by 100 matrix is just ones, and the second one is just x's. I will call this phi of capital X, there's a big X below, for whatever the x's are. That's a matrix. And then we can talk about both function values that lie in the reals. So a single function value. F is a real valued function, right? It takes in a real number, it returns a real number. F of x is some number. But we can also talk about f of, let's say, capital X, which is the inner product between this feature vector and the weights. So that's this transposed, right, 100 by 2 matrix multiplied with the weights, which gives me a 100 element long vector of function values. It's all just linear algebra, it's all just multiplying vectors with each other, but it's a very convenient thing to do. Now I have a stack of vectors. And that's how I made the plot. So for that, I'm going to use this notation, which is quite common in this community of people doing inference on functions, regression. And it's very convenient. Why? Because you can think of these x's here as the index set, the indices, into a discretized vector of function values. Right? If I evaluate the function x at many different values, then I get a vector that is indexed by the locations. So just like you're usually thinking of a vector as indexed by 1, 2, 3, 4, 5, 6, 7, we're now actually directly indexing it by a different index set, which is the values of x that we're feeding in. And so maybe arguably a function is like an infinitely long vector, right? It's a bit like I have to do scare quotes when I do that, because of course functions are kind of potentially dangerous objects, as we discovered in the second lecture, but basically that's the idea. So our code for the prior looks like this. We're taking in we're loading the stuff that I also just showed you on the other slide. We define the prior, which is what I just showed you. Then we define this function space, and we can now create a prior in function space. Okay, that we've already seen. I've shown you the code. Now, let's work with data. So what we've just constructed is a prior distribution. And we can think about this prior distribution equivalently in two different spaces, either in the space of these two-dimensional weights or in the space of function values, arbitrarily many function values. I mean, I decided to discretize it on 100 grid points, but of course, I can do the exact same thing with 1,000 grid points. And these grid points don't have to be regularly spaced. They could be wherever, right? Now, I make this observation. I observe that the outputs y are measurements of this function f of x with Gaussian noise. So how do I do inference? Which theorem do I have to use? I know it's a silly game, but please. Bayes theorem, yes. So, of course, because there's no other theorem to do inference, that's it. Anytime you don't know something, Bayes theorem has to show up. So we're going to multiply this prior with this likelihood. Notice that this likelihood is exactly of the form we need. It relates the unknown stuff w to the known stuff y through a linear transformation. And that linear transformation happens to be this vector of feature functions, phi of x. So here is a little, you can think of this as a matrix A. The matrix A now happens to be called AX, phi x. And it's Gaussian. So Gaussian prior times linear Gaussian likelihood gives a Gaussian posterior. And we can read off from this busy slide at the beginning of this lecture what the posterior looks like. It contains all this nasty stuff, right? So the posterior over the weights will be another Gaussian. It'll have a new mean and a new covariance. And these objects will have these complicated linear algebra expressions in them. But we've now stared at these already. We spent the whole lecture thinking about them, right? We know that to get the mean, we have to compute this residual between the observations and the predictions. We have to scale them by the inverse of this gram matrix and then project them back out into the space of W. We know how to do that, right? We can compute a posterior on W. And actually, we don't even need to do that ourselves. We can just call our cool function called condition, and then it'll work. When we do that, we'll get a Gaussian in a two-dimensional space back, right? It's just a two-dimensional Gaussian. It's conditioned on how many observations we've made. In this case, I think it's 20. There are 20 numbers in this plot. We make 20 observations, so y is 20-dimensional. This is a 20-dimensional vector. This is a 20 by 20 matrix. And now we project back out into a two-dimensional space. And this is a case where it's actually easier to do the computation like this. But we just call our code. We stop thinking about it. Now we have a 20 by 20, a two-dimensional Gaussian. How do we get back out into function space? How do we make new projections into functions of f of x evaluated at many points x? We could sample from the posterior, and then every single sample amounts to a set of weights that gives us a function, yes. But do we need to sample? No. We do the exact same thing as before. We just map it back out again. We just build another feature vector, push it back out. So here is the code for this. And I'm going to show it to you in a second also in a live Jupyter notebook. This bit you've already seen. Now, so this is sort of the generic, the template picture for supervised machine learning in the probabilistic perspective. We begin with a prior. We say, this is our model. That's why it's called a prior, right? You do it before you see the data, at least, if you're sort of philosophically clean. So we write down the model. We say our model is that there is some function that is unknown. It's a linear function of x. It depends on two numbers, a constant and an intercept and a gain. So by writing down the feature functions and the prior on the parameters, that's our generative model for function values. Now we load the data. We do that with like this little bit of pandas foo. It's like the nasty stuff, I/O, right? It's always a bit, it's like some long number, some long line. We also write down what we think the noise is on each of the measurements. The standard deviation here is 1.5 in this particular data set. Now we do inference. That's Bayes' theorem. This line here, that's what Bayes' theorem looks like in Python. Now that we've written down all this cool code, now that we spend all this time building this Gaussian machinery, which is say, take the prior, condition it on linear observations. The linear observations are encoded here. So we take the inputs x of the data set, we feed them through the features phi. That's our linear projection. The observations we make are y, the data. And the noise is this diagonal covariance matrix, which says we are assuming that we make every single observation independent of the other ones. That gives us a posterior distribution that is a Gaussian. And it's a Gaussian over two random variables, W1, W2, or W0, W1, depending on how we index. And now I want to make a plot. So I take this two-dimensional Gaussian and project it forward into this function space. OK, let's do that. So actually, I'm going to comment this out again so that we don't have this long line. Here I do exactly this. So I load the data. This is a vector, this is a vector, that's a scalar. I condition this. And now we can ask, actually, what does this posterior look like? It's a two-dimensional Gaussian, right? So the prior, remember, had 0 mean and unit covariance. The posterior now has a positive intercept. So it thinks that the function passes just north of 0. And a positive gain, of course, that's what we expected from the data. And the covariance is now a positive number here, some tiny number on the off-diagonal, and another positive number here. These numbers are much smaller than before. Why? Because we've learned something from the data, right? We're now much more confident. OK, so I can make this posterior over the function values. If I would plot that, what is it going to look like? Just so everyone follows along what the data types are that we're constructing. Still a Gaussian, but over some very high-dimensional space, right? It's a 100-dimensional Gaussian suddenly. So if I plot it out, it's just going to be ugly, right? Just fill the screen. And now I'm going to make a plot. So I'm actually going to define a little tool that I'm going to keep calling. Let's spend 2 minutes thinking about it. I'm going to take I'm going to write a function that I'll keep using that sort of reproduces this process. It takes in a prior, a model, so a linear, like a feature function, phi. It takes in the inputs x and the outputs y of our data set and the noise. And then it takes internally, it does exactly Bayes' theorem. So this line is called Bayes' theorem. Then we make a plot. We compute, we make this sort of, we make a plotting grid from -5 to 5. We do this projection into the function space, both for the prior and the posterior. And then we'll make 2 plots for, so that's the 2 here, right? 2 plots on the left and the right. And in each of these, we will plot a Gaussian, for which I have a little Gaussian plotting function that you can have a look at. In the Gaussian thing, it just makes a nice little plot with, the one with a mean, and 2 standard deviations, plus, minus, and it shades the area in between with the PDF of the Gaussian. Then it also plots the data so that we know what's going on. It plots the features, phi of x. What is phi of x in our model so far? Remember? It's x and 1. Yeah. So it's a constant function at 1 and the linear function x. F of x is x. Just a straight line. Okay? It makes this plot. we label the data, we set the parameters so everything is kind of nice. And now I should probably make a plot. Oh, what did I copy? Did I not put this in? Okay, so I should probably make a little. Can I do a? Can I call this? This is going to be nasty without seeing the plot. Okay, we will need our prior phi, x, y, and sigma. Actually, this might just work with a lowercase s, of course. Oh yeah, thanks. See if this works. Yes. Woo. Okay. So lucky. Okay. So on the left, you see the prior distribution. That's the one we've already looked at before. I've just used different color maps now. So in the back, in blue, you see the feature functions. There's a constant function in blue at 1, right? And then there is a straight line function phi of x that's equal to x. Then you see in black the prior mean, which is 0. So it's the prior prediction for the function values at x are always 0 because our prior mean is 0. Then as a dashed line, you see plus minus 2 standard deviations of the prior. And as a shading in the background in green, you see the probability density function of every single marginal Gaussian distribution. So at every single point x, there is a one-dimensional Gaussian distribution, a bell, right? A bell-shaped thing that goes from minus 2 standard deviations through the mean to plus 2 standard deviations. So if you made a cut through this plot, you would get a local Gaussian little bump, a tiny little Gaussian bell curve, right? And the only thing that changes here is the standard deviation as we go along x. I also drew 3 samples just for the hell of it, because why not draw 3 samples? That's these thin black lines here. And that's the data. Now we condition on this data set. This is our posterior distribution over this function. It has a mean function that is now actually non-trivial. So for every possible value of x, we get a different mean prediction. And we get much, much narrower posterior standard deviations. And this is our prediction for this unknown function given the data that we've seen. Question? No? Everyone? No. Okay. Yes? So the question is, why does this posterior look like this little trumpet-like shape, right? Why is it narrower towards 0 than further out? Well, think again about what we're doing here, right? We have these two, inside of this model, there are 2 unknown numbers. The weight for the constant feature and the weight for the straight line, x. So we're actually still uncertain about either of them. We don't know them perfectly yet. So in particular, there is one term in here that just adds a constant uncertainty at every point. It's just a finite width that's constant everywhere. But then there is this weight that goes into x. And as you can see, the variance will be something like x squared, right? So there's actually still this sort of unknown number in here, right, that scales like x squared. And that, then we take the standard deviations, we take the square root of that, so the x squared sort of almost becomes an x, right, plus the unknown constant. And that's why we get this uncertainty that keeps growing linearly as we go away. Asymptotically, it grows linearly. I mean, towards around 0, it has this little bend shape. Yeah. Because at 0, this term is 0, and then we still have a constant. Okay, that was a deliberately very slow progress. But as we did all of this, I mean, of course, I know linear functions, trivial. But as we did all of this, I tried to convey really what's happening inside of our machinery. So after the break, very quickly, we'll make things a lot more complicated, and we'll just keep using the machinery that we've now built and just change inputs into our code. And it'll make suddenly for a much more powerful tool set. So now is the question for me to, like the point for me to ask, are there any questions? Was this all super obvious? Are you following along? Because like so far it seems very easy, right? But that doesn't mean that the mechanisms are all that obvious. Yes? So the question is again, how does this two-dimensional distribution over weights induce a, well, seemingly very high-dimensional, or actually is a very high-dimensional distribution over function values? Let me go back, maybe, Okay, so depending on what exactly you're unclear about, you could either look at the math or at the code again. So let me just maybe do 1 minute each, right? And then we'll do a break. So we started, well, actually, let me do this picture. That's maybe the best thing to show. So there is a two-dimensional space that describes everything we don't know. Actually, there are two things. Well, no, there's only two things we don't know, right? There's just two numbers. We have made the assumption that the function we want to learn is a linear function. Linear functions have an intercept and a gain, right? So they have the value they have at 0 and their derivative, how quickly they rise or fall. So we can describe all of this in two numbers, but the observations we make depend on x, through the fact that the function we're trying to learn is assumed to have the form w1 plus w2 times x. So what I've done is I've written this 1 plus x as a set of features that can be multiplied with these weights. And if I do this for many, many different x's to make a plot, then this phi of x becomes a matrix. But it's still a linear map. And I'm literally just using the properties of Gaussian distributions, that a two-dimensional Gaussian distribution projected into a 100 or a 100,000 dimensional space is still a Gaussian distribution. So for those of you following along on the linear algebra side, you can think for yourself about what the rank of this covariance matrix is. I mean, you can probably guess, right? But just because that rank is not the number of plotting points here doesn't mean that we are not getting something interesting to plot here. Rank-deficient matrices are quite fun sometimes. Okay, so now what I'd like to do is send you into the break, but of course not without something to think about. So we've now built this code, and of course in your head you're already going, yeah, linear functions, come on. Huh? So what about if I give you this data set? This is clearly not a linear function, right? What do we do now? Was it all in vain? Do we have to throw away all this Gaussian stuff and do deep learning? Think about that, and we'll see each other in 5 minutes. So there are some really cool questions during the break that I want to relate to you as well. So maybe let me go back to this picture, and I'm going to play around with this a bit. Okay, so let's do a different prior. I will make this a Gaussian of mu equal to okay, this is so difficult to do with. Okay, what is the plot going to look like if I create the prior like this? Yes, someone is doing like this, right? So what I'm doing is I've only changed the mean. Before the mean was 0. Now I've only changed the second entry. The second entry is the weight for the gain of this function, right? And so I'm assuming a priori that this is a function that has positive slope. And nah. Right? So now the prior distribution already looks like something that has positive slope. I can also put a -10 here what's going to happen now? The whole thing will shift down, only down, right? All the way down. And actually, the data is so strong that the posterior will basically be the same, because there's so many measurements, 20 different numbers, nothing can go wrong. Actually, why is this the case? That's what this picture here is supposed to be about. Let me see if I can draw this here. Actually, let me go like this. So I think, again, there are several people confused about what happens in this two-dimensional space and this higher dimensional space. So here, first of all, so in this space of function values, so this is f of x, and this is x. At any point x in this little posterior distribution, at any point x, if we cut through this distribution, we use this property that marginals of Gaussians are Gaussians. So we just select out a one-dimensional Gaussian, and it's just a Gaussian. It's just a bell-shaped curve, right? So if you would plot along here, you would get some kind of bell-shaped curve that looks like a Gaussian. And here it's a bit wider, and here it's a bit narrower. When you make a Gaussian narrower, it also has to be higher in the middle because it's a probability density function, so it has to integrate to 1. That's why in these plots, where the plot gets narrower, it looks a bit darker. So what does this look like in weight space? I used to have a picture for this, actually, and then I took it out for this here because it seemed too confusing, but maybe it's not. So what's happening in our weight space as we get observations is we start with this Gaussian prior, standard Gaussian prior, just a, circle. Now we make our very first observation. Let's say it's at some x value, I don't know. It's at 1. We make this measurement of y with this Gaussian noise. Then if we have a positive observation at a positive value of x, that's indicative of either a positive intercept or a positive gain, right? And if the gain is high, then the intercept could be low. If the intercept is high, then the gain should be low. So we get negative correlation. The likelihood that corresponds to this one single observation is a Gaussian likelihood. Remember that likelihoods do not have to be probability density functions in their right-hand side. This Gaussian likelihood actually looks like sort of this. That's the mean in the middle, and then one standard deviation to the left and right. It's still a Gaussian function, but as a function of x, it doesn't look like this bell-shaped thing. It's just a Gaussian in y, right? So along here, it's a Gaussian, but in x space, it doesn't look like a Gaussian. So what we are doing is we're multiplying the prior by the likelihood and normalizing. That's Bayesian inference. So we multiply this thing by this thing, and it's another Gaussian, right? It's sort of maybe this thing, right? That's our posterior. And now in comes another data point. Maybe it's at -1 and plus 0.2. Then that's indicative of a positive slope or a positive intercept. And so this will look like, now maybe you're beginning to understand why I took out this plot, because it gets very busy. One more likelihood term. We put it in, we multiply by this so far posterior, we get another Gaussian. We do that 20 times with our data set, we get exactly this plot that we just looked at. Okay? Good. Now, I showed you this. I said, what are we going to do now? Are we screwed? We need to train a transformer. Quick! No, I'm only partly joking, because it's really this knee-jerk reaction sometimes, right? So what do we do if we have a nonlinear function? Yes, please.
Construct nonlinear features?
Yes. So far, construct nonlinear features is the answer, right? So far, we've used this assumption that this is a linear function of x. But remember, the only thing we used, the only property of Gaussians we used, is that the observations we make are linear projections of the parameters of our w's, of our weights, w1, w2. The fact that this function happens to be linear in x is completely irrelevant. It's actually it was so basic that it almost felt like overkill, right? So we can just use some other features. What other features would you like to use? Yes, please. X squared. Perfect. Perfect answer. That's actually what I did. So here I'm doing this. Let me go. Now I have to sort of be careful with the reveal. So I'm loading this data set in this cell, right? That's really it's just loading this nonlinear thing. So I'll call them xn and yn, n for nonlinear. Yes? Make it larger. Yeah, I can do that to some degree, but then I'm gonna have to scroll up and down with the plots, and so maybe this is just enough. Okay, so now I've loaded this data set. If I do this with, actually, let me remove this prior again, or set it back to 0 so that this thing works. So if I use this prior again on this nonlinear data set, then first of all, let's confirm that the posterior is kind of stupid, right? So this is not going to work if you just keep making this linear assumption. This is maybe actually useful to make this observation for once, right? If you're making silly assumptions, Bayes' theorem is not going to save you. Garbage in, garbage out. If you're assuming that this function is linear, what's the model supposed to do, right? You're giving it a language that has to describe what you're doing in terms of linear functions. There is no way out. You have to find a linear function. So what we're finding is the best possible linear function that explains this data. But of course, it doesn't explain the data. It's completely off. So there is a perfect proposal. Let's use, that's just a helper function to make a good prior. Let's use more features. In particular, let's maybe use polynomial features, right? So instead of just 1 and x, I'm going to use 1 and x squared. And I do this here. So I'm defining polynomial features, which is a function that takes in x, and then I tell it how many features to use. And then what it returns is a vector that contains x raised to the power of a range. So raised to the power 0, raised to the power 1, raised to the power 2, and so on, right? Which makes this vector 1x, x squared, x cubed, x fourth, and so on, depending on how many features I use. So if I use just 2 features, that's exactly the same thing as before. But if I set the number of features to 3, it's going to produce 1, x, and x squared. And then actually, to make things a bit more stable, I'm dividing by, this is a fancy way of writing divide by the order of the polynomial factorial. Because just like in Taylor's theorem, right, you want to have the higher order features dampened by some term, because otherwise the higher order polynomials will dominate everything. And then I'm also dividing by the number of features so that I can smoothly decide how many features to use, and things will stay the same. And here's what we get. So in the prior on the left again, and the posterior on the right, in blue you see the features. There are now 3 features: a constant function, a linear function, a quadratic function. And the prior now looks like this. Why? Because we now have a quadratic feature as well, which opens up this trumpet a lot more. So the prior actually kind of looks okay, right? It kind of has this expanding thing on the left and right. But the posterior is maybe a bit overfitting. Okay, maybe that's just because I'm using only 3 features. Let's see what happens if we go to all the way to the 6th power, right? Ooh, can we do that? And we get, okay. So now we have 7 features, right? The constant function, the linear function, the quadratic function, the cubic function, quartic function, quintic function, septic function. And here is what the posterior looks like. It's a little bit more flexible. Looks a bit better. Okay, are you happy with that? Should I try more features? Can we do more? At some point it's going to break, just numerically, but I can try 20. Oof. Right? Now we have 20 different features here. That's as many as we have data points. Can I use 40 more features than data points? Am I allowed to do that? Fit a 50-dimensional polynomial? Am I not allowed? Am I allowed? Of course I am, because it's Bayesian inference. Then nobody tells me that I have to have less parameters than observations, right? I define the prior with 0 data points. I can do that. It's just, okay, it's just that it gets a bit boring, right? Okay. Any other ideas? Maybe those polynomial features are, we've now done what we could. Other proposals? Can we do something else other than x raised to some power? Yes. The sine and cosine. Do I have this? Woo, I have it. Good. It works every time. So now I have new features. I actually use cosines, not sines. I'm sorry. So I decide to use 10 different cosines. The feature function takes in an x. And then what it does is it takes x, it multiplies by pi, because then things have the right frequency. And it takes the cosine of that, but before it does that, it divides by the number of features, that's the frequency, divided by, sorry, a range of the up to the number of features times a constant. So this means I'm going to create cosine features with varying frequency. The first one will be basically a constant function, right? The cosine of frequency 0, and then the standard cosine, and then a faster cosine, and so on. Okay, I'm doing that now. Everything else is the same. So this is what our prior now looks like, and that's what the posterior looks like. So in blue, you see initially this very broad cosine, and then increasingly higher frequency cosine functions. This makes this cool looking prior. Somehow there's a lot of mass at 0. And this is what this posterior looks like. Whew, not so nice, right? So one problem with cosines is that they are symmetric functions around 0. And that very much restricts the functions we can learn. Every function we learn has to be symmetric around 0 as well. How can we fix this? What's the problem with the cosine? What does it need to be a full basis of an interesting function space for the mathematicians? Yes? Yes, we also need sines, right? Because the sines are the antisymmetric functions that pair to the cosines. And the sum of an antisymmetric and a symmetric function actually is enough. Then we can get everything. So I'm making trigonometric features, which is the same as before. I now just stack the cosine features from before on top of a bunch of sine features, right? And now our posterior will look like this. So now the feature functions in blue are sines and cosines, right? And this is what the corresponding prior looks like. Nice, smooth functions. All these functions are periodic because they are sums of periodic functions, finitely many. And we get this posterior, which is a nice red curve going through the data points. Quite nice, actually. Maybe I could use maybe a bit more, maybe not 10 features, but I don't know, 40. Then the plot will get a bit busy, but. So now we have this nice, cool interpolant. Be happy with sines and cosines? Is that enough? Some of you are already thinking, is this doing some Fourier expansion? Yes, it is. But any other ideas? At this point where this is the usual ideas, right? So either polynomials or sines and cosines. Any computer vision experts here? What's your proposal? Exponential functions. So many exponential functions. So every single one will be like an exponential. I invite you to try that. So if you're maybe thinking a bit more in sort of discrete spaces, images, pixels, then maybe you could say, actually one thing that sometimes people suggest then is because they've had a deep learning class is, how about ReLUs? I've heard ReLUs are good. Let's do ReLUs. So here I've defined ReLU features, which are just a bunch of, ReLUs. So ReLUs are these piecewise linear functions that have a hinge, a kink. I've done this here. So here I've set, I think, 8 different ReLU functions. I make them such that half of them point one way and the other half the other way, because otherwise we'll have a lot of zeros on one side. We get, it's maybe not a great prediction because it has these kinks, because there are 8 ReLUs in there, and that means there are 8 kinks. But otherwise, it's actually kind of nice. So maybe I can make a few more, actually 10 ReLUs. Let's maybe use 20. This is not so bad, because one nice thing about ReLUs is that, well, maybe nice, I don't know, it's a property, a feature of ReLUs. Maybe it's a bug, maybe it's a feature, is that they are growing without bounds towards infinity. And that means that this function can extrapolate linearly upwards, like a rocket going up. Right? It doesn't have to come back down again. which is maybe nice for this data set because it seems to have this takeoff phenomenon there, over there. Then one more thing one can try is sigmoids. People then sometimes say, hey, tan H, you know, sigmoid. Okay, yeah, so here's a bunch of sigmoids. You can barely see them because they're scaled down. So each of these blue lines is one of these S-shaped functions, right, like the logistic. One nice thing about sigmoids is that they're very smooth. They make smooth functions. So here are very smooth functions. But because they're so smooth, they're strongly over-smoothing here, but I could fix that by setting the scale to something less. Num features, the L should be 0.1 maybe. Like, so now they're a bit steeper. Now we get steps. But there are not enough of them, so we should have more, maybe 20. I invite you, I'm showing you this plot because I want to get you motivated to have a look at this code yourself. It's on Jupyter Hub. You can just do all of these changes yourself, play around with it. Right? Now, one thing that I quite like, and you may find out later in the course why, is step features. So what I do here is I'm saying I'm going to build features that are just 0 to the left, and then they switch on, and they become 1 after some point. And now I make a lot of these next to each other. So each of these looks like, actually they are the kind of step functions that come in from +1 and they go to the -1, or they come from -1 and go to +1. So they are sort of non-zero everywhere, which gives this pixel-like behavior. So these don't look nice, but they're actually quite a powerful framework because counting measures are a really powerful thing to use. They look ugly, but they're quite powerful. Another way of doing this is what I call switch features. So they start at 0 and then they go to 1. And now I'm using a lot of them, 100. And you can see that sort of they all start at 1 point. So beyond here, beyond -5, there are no features. They're all 0. But then at some point, things switch on. They start moving. And then at every single tiny step, out of 100, I've put 100 there, I think, one of these features gets switched on. And every time we go, one more gets switched on. And so you can see that their number grows, right? And as we go to the right, more and more of these are switched on. And we keep seeing more and more flexibility in the model. Question for you is, how quickly does this curve grow? It's clearly not a linear function here that's going. So you can think about how quickly it grows. There is a deep-seated insight behind that. Very deep. Got a Nobel Prize at some point. So long time ago, over 100 years. And name of that guy? Albert Einstein. And so here is the corresponding posterior. We'll talk about this later. Okay, maybe I can already tell you. This is connected to Brownian motion. Right? So the model that's happening here is, you can imagine every time step, you could call this axis time, and every time step, this function gets a little nudge, either up or down, and the nudge is random. It's a Gaussian random variable. And that's just like Brownian motion. That's exactly Albert Einstein's model of Brownian motion that he got his Nobel Prize for, the only one he got. Final thing is we could use what's dangerously called Gaussian features. And I put them at the very end deliberately because otherwise you would have thought that somehow Gaussian features are necessary to do Gaussian inference. But they're not, of course, right? You've seen all the other ones. But I could also say my feature functions themselves look like little bell-shaped things in X. And that's what I do here. So I say, as a function of X, put a bunch of center points from -6 to +6. And then across that domain, put little bell-shaped things next to each other. Why is that good? Well, it's good because it's somehow localized, right? There's sort of these local interactions. They're also very smooth, so they're going to make very smooth functions. And people like that, so we do that, and here we go. So this is a very popular choice for regression in low-dimensional spaces, like here, one-dimensional space. It makes smooth functions, looks smooth. You get this nice, okay, yeah, smooth curve. You can do all sorts of crazy other stuff. So I have here, for example, also loaded some crazy polynomials. Maybe you've heard about orthonormal polynomials in your chemistry lectures if you've taken an undergraduate chemistry class or physics class. Here are Laguerre polynomials, I think. No, Chebyshev polynomials. There are a lot of them. You could try Laguerre, Hermitian polynomials, and so on. They're only defined on a bounded domain. They're orthogonal to each other, cool tools, and they make these very interesting interpolants that have been studied in math for a long time. Some of them form the basis of the models for the hydrogen atom, for example, and so on. All of these tools have been used in science for many, many different applications like this. Yes? How are these different from the ones that I used before? It's a different set of polynomials. Yes, so the polynomials I've used above are these classic monomials, so it's just x to some power. These here are differently parameterized polynomials that are orthogonal under some other measure. So in functional analysis, right, those of you who have taken a functional analysis class, you know that there are these different bases of function spaces, and they often take the form of these polynomials, and they have a lot of historical relevance, like, for example, in chemistry and physics, and, you know, and you have just picked some. So they're also used in numerical integration. If you've heard of Newton quadrature, then, you know, you've heard of Chebyshev polynomials, Gauss-Chebyshev, and so on. These are all these ideas. Okay, so I want to tell you two more things. We have a little bit of time. One is, here's a little mental exercise for you before you leave later on. Maybe you're thinking, okay, but it's one-dimensional, right? That's boring. Nobody wants to do one-dimensional regression, right? We want to learn labels of ImageNet. ImageNet has millions of dimensions. How is this relevant? Matthias Heines told us already about high-dimensional stuff, right? So for that, maybe let me go back to my slides and point out that all you need is a feature function. So that function takes in x, and then it returns numbers, real numbers. What that x is up to you. So this function phi maps from a space called feature space into the multivariate reals, right? Into R to the f. How it does that? Completely up to you. So think for yourself how you would do this if x is 2-dimensional, 3-dimensional, 10-dimensional, 784-dimensional, or 1 billion dimensional. Doesn't matter. Completely irrelevant. Actually, if you want to have your mind blown, you can even do it the other way around. What if you wanted to predict a curve? Something that doesn't just have a real value as its function value, not a single scalar y, but a 5-dimensional y. How would you do that? Just think about it, okay? So as you'll do that over lunch, let me quickly make the connection back to the stuff that I bored you with last week, because now we're at a point where we can actually do this in 15, 20 minutes properly. So why was what we did last Thursday relevant? Why did I bore you with this? Well, on Thursday, let me just quickly recap. I pointed out this massive piece of thing that I just copied again that said linear algebra, the computational routines, not the stuff that makes nice pictures, but the stuff that happens inside of this cool machine here, that the computation itself, linear algebra is just Gaussian inference. Solving a linear system of the type A transpose times x is equal to b, solving that for x, is a form of Gaussian inference. And the algorithms used for that, like the QR decomposition, the Cholesky decomposition, the LU decomposition, and so on and so on and so on, they all are different strategies for collecting linear Gaussian observations of x. And we realized that we can get all of these different models and methods by picking particular policies, building a little active learning machine that follows some policy to select views onto the data set. If we do the naive thing and just select one entry in the data set after the other, so if the S's are just the elementary vectors, elementary basis vectors, then we get the QR decomposition. If we pick the S's such that they do basically the same thing, but they correct for what you've seen before, so they do the Gram-Schmidt process, then you get the LU decomposition, and if it's a symmetric matrix, you get the Cholesky decomposition. If you pick the S's to be pointing along the residuals of your current estimate, so along A times your current mean minus B, you get a method called conjugate gradient. So we can think about all of these methods as actively collecting information about our data sets, as data loaders. And I want to do this at this point of the lecture because in the deep, complicated deep learning world, people have sort of accepted that the data loader is just this fancy I/O routine that runs on your hard drive to select batches from the hard drive. In this basic setting where we can still think and not be completely overloaded by all these complicated models, we can actually think about how to efficiently load data and whether we are allowed to stop loading data at some point, whether we always have to look at the whole data set or whether we can stop, or whether we can maybe produce views that are particularly useful. So how do we do that? Well, the question that we have to answer to do that in the context of today's lecture amounts to, well, these probabilistic linear solvers that I talked about, they are subject to these prior parameters, to the prior mean and the prior covariance. How do I have to pick those to get an algorithm that actually makes sense? If I just set them to some number, I'm just going to get some estimate. How is that going to be useful, right? I want to make sure that the uncertainty I get is actually useful. So it turns out that there's a way to do that that was actually only introduced like 3 years ago in a new RIPS paper. And it works as follows. So in the stuff that we did today, all these pictures we just looked at, I made them easy for you by writing down this Python code and just saying prior.condition, right? But what actually happens inside of this nicely encapsulated piece of code now, so by the way, right? So this code now looks really complicated. So I have this here. These Gaussians that have been developing over the past 2 weeks, right? We still have this code, this object, and it's now quite complicated by now, right? But we started 3 lectures ago, and it just kept growing. So we have this stuff in here called condition. Where is it? There. No. What? Hang on. Sorry. Condition, right? That's the code that we called. And it does this, it actually, in this form, it does this Cholesky decomposition. It calls some low-level routine. And then the downside, I argued, of doing things this way is that you then just have to accept whatever this routine does inside. It's like saying, oh, take a standard data loader from PyTorch. Let's just hope it works, right? That's the corresponding thing to what we're doing here, just in a numerically stable way. So what I've now added is this thing, which says we can also condition using a probabilistic linear solver, so using Gaussian inference itself, using the algorithm that I introduced last Thursday. And that algorithm is now also in here. You can find it down here. It's now stored here at the bottom. Here's this GEQRF function that I introduced in the last lecture. And there's a generalized version of it, GEPNF, probabilistic numerical factorization, which has this policy in it. It takes in a policy and then does this stuff. So I showed you the corresponding code on last Thursday, and I'm not going to bore you with it again. So what these methods do is you tell them that you want help in this part. Right? So we're doing our regression. We make these little plots with that we just looked at. All of these plots, they all were internal calls to this piece of linear algebra. And that requires us to take this residual, which is a right-hand side b, and then find the vector x such that a times x is equal to b. So it's exactly of that form that these linear solvers can give us. So this is the matrix that we're going to run the algorithm on. That's our A, and that's our right-hand side B. And then once it has done this computation, we also want to use the information collected about the structure of this matrix to also solve this problem back here. Right? They also get posterior uncertainty. And I always made this point that it's nice because if you've found the matrix decomposition of this matrix, then you can reuse it over here to also get uncertainty for free. So how do we do that? Well, so we're going to run our solver, this fancy machine that I just flashed at you, that will take this A and the B, and it'll return an estimate, which I now call Z, so not confuse you. It used to be called X, but we already have X's in our regression problem now, so I'm just going to call it Z. So that will go in here to compute the mean. And then to get our posterior covariance, we need to be able to do this. So that will be a call to our solve method. Right? It'll say solve on a different right-hand side with a different b. The right-hand side is this thing. So when we do that, we get these objects that the solver returns showing up in our posterior distribution, in the mean and in the covariance. So now the nice thing is that our solution set actually shows up linearly in the mean. So in this Gaussian random variable called posterior distribution over the weights, there is another Gaussian random variable, and we depend linearly on it. And that means we can marginalize out that unknown Gaussian random variable. So we can do that back here. That's actually a little homework exercise for you. It's just that one-liner, basically, or two-liners using the properties of Gaussians. And we'll get a posterior distribution over the weights. That's a typo. This should be a W here. I'll fix that. With this mean and this covariance, where this is the mean of our solver. And then there is a correction term, so that there's a posterior covariance that involves both the unknown matrix inverse, which we don't have, and the posterior covariance of our solver. So that structure actually gives us a hint for how to pick the parameters of our solver. And that's already an argument I tried to make last week, but then I ran out of time, so now I'm going to make it in 2 minutes. My argument is going to be we should pick the parameters of this algorithm, the learning machine that sits inside of our little Gaussian object, and set them to the prior mean to 0 and the prior covariance to this unknown inverse of the matrix. At first, that sounds super counterintuitive. Why can I set the parameters of something I want to work with to something I don't know? Well, because it turns out things cancel out. If we pick the prior mean to be set to 0 and the prior covariance to this unknown matrix inverse, then in our prediction for the weights of this regression model, in these plots that I just showed you, actually has the property that at initialization, when we start the algorithm, the mean that we get from marginalizing over the uncertainty of the model is just the prior mean. So that means before I start the algorithm, it doesn't do anything. It leaves my prediction unchanged, which is what I want, right? I want to have an algorithm that doesn't already change the prediction before I started using it. And then in the prior covariance, these two matrices will cancel, and I'll just get the prior covariance out. So at initial, I just get what I want. The algorithm is not doing anything. And then, as I keep running the algorithm step by step, what I will actually get is a tractable mean, of course, at any point in time. And in the covariance, exactly the right terms will cancel. And the only thing left in the posterior covariance affected by the solver are these quantities, which are admittedly a bit too fast for you now to grasp, which happen to be the stuff that the solver already knows, the projections along which it has run. So in short, what that means is my final slide, and then I'll show you a plot, is what we can do is we can call inside of our Gaussian conditioning routine this probabilistic linear algebra routine, which is another Gaussian inference routine. It'll take care of the solve for us. It'll do its QR decomposition or whichever decomposition we like, Cholesky, conjugate gradient, whatever. And then its solver function that it returns can be used to compute both the posterior mean and the posterior covariance in such a way that at initialization, the algorithm doesn't do anything, and after, as it runs, it gives us a calibrated posterior. There's even theorems that you can find in the corresponding paper, the one up here, that shows that this posterior is actually calibrated in the sense that it's always a worst case bound on the actual error, and so everything kind of works out fine. So what does that mean in practice? That I just want to flash at you. Let me go back to this thing that's actually at the end of this notebook. You will be able to find that. What I'm showing you here is on the left again the prior for this regression problem that we just solved, again using these Gaussian features that you just saw at the very end. And here is the posterior from a standard linear algebra routine, a direct solver. So a Cholesky decomposition of the Graham matrix. It's just this black box thing that does its magic for you. And here on the right is the posterior you get from this routine, this linear algebra as Gaussian inference routine, using, in this case, a policy that's called Cholesky, and I'm going to call it with false. So that's the routine that just goes through the data points one by one. And now we're at 0, so we haven't done anything yet. In the very first step of the solver, bang, it picks the first datum and conditions on it. And then on the next step, it takes the next data point and conditions on it. And then the third one, and then the fourth one, and the fifth one, and so on. OK, so first insight, there's actually a way to using these, like to breaking up the black box linear algebra methods that allows us to stop at arbitrary points in time. OK, so far that's a bit boring because I could do this from the outside, right? I could just say, well, OK, just use the first 5 data points. OK, I can give those to my Cholesky decomposition. Now, a slightly smarter thing to do is what's called pivoted Cholesky. So I'm going to say, please, little routine, as you work, go once in linear time through all the data points and check which of them has the furthest distance from your current prediction. Which one has the highest residual? So initially, that's this point up here, right? That's furthest away from the prior mean. And let's condition on that one first, because it seems to be the most important one. Bang. And then, which one is the next one that's furthest away? Actually, I don't know. It's probably somewhere. It's probably this one, right? Then let's condition on that one. And then whichever one is next. And then this one, and so on. It's all a bit slow because I really didn't pay attention to make this code run fast. But this is a policy that picks data points in their order of importance, right? How far they are away from what we predict. And you can see that the corresponding uncertainty behaves well in a good way, right? So we actually contract as we go in. Actually, if I keep doing this for like the whole time, right? If I go all the way to the end, then after this is all run, I will obviously get back. It takes a bit of time. There we go. I'll get back the exact posterior, right? So that now these two plots look exactly the same because I've gone through the whole data set. Okay, obviously. But I can also say something, I can also use things like stuff that I couldn't do from the outside. I can run a method that follows the gradient of the error that always picks linear projections onto the data set. So a data loader that doesn't load batches, but it loads linear projections of the data set that are maximally informative. Whoops, I'm sorry. So after the first observation, this method will already make a correction like this. This has loaded a single view on the data set, like a single scalar. It just happens to be a very smart linear projection. That's a rank 1 update. It has cost O of n squared times 1. So memory cost O of n. And then if I do 2 steps of this, it's already pretty good. And if I do like 5, 6 steps, the posterior mean will be pretty much perfect. The uncertainty is still relatively high because this model the algorithm has to discover that it has already learned everything, but it's essentially done after like 3 steps. Wouldn't it be nice to have this kind of functionality in deep learning as well, where we have some routines that go through these large corpora of language and images and so on, and provide projected views into like the core of these data sets? That's what we would like to have, and in 2025 we don't have it yet. But we're beginning to see how to do this in like, one-dimensional plots that look a little bit like this. Okay, so I wanted to show you this, and now I'm done. My point today the main point was, we can learn functions purely with Gaussians. And the way we did that is to write down feature functions in a parametric way. So we decide how many numbers we're going to use to represent the function, the number of weights, and which features to use. We discovered that we can use pretty much any features, any. Sines, cosines, step functions, discontinuous features, non-differentiable features, features that go to infinity, features that return nons. If you're careful doing the internal code right, you can use anything you can think of to learn functions. And on next Tuesday, because this Thursday is a public holiday, obviously you all know, next Tuesday, we're going to think a bit more about what we're actually doing here, and if the code that we've written so far is the most elegant way of doing this. Maybe you can already think of something smarter than the way that I did it. Please give me feedback. I hope that you enjoyed today's lecture a little bit more than last Thursday. I'm looking forward to see you next Tuesday.